Okay, let's start our session today. So I just, all of you hopefully got the grades for exercise set 3, and all of you have done pretty well, considering I think this was a very challenging set in particular. So, but I just want to take a joint session just to discuss. Maybe already some of you already know everything, are completely clear about the exercise, but just to kind of show how the results should look like. Okay, I don't have a for many of these problems I don't have a solution. You are the ones supposed to make the solution for the future. Okay, so I cannot say it's 100% right. Okay, there might be a small error, a small mistake, but at least it looks everything checks out. The review that I and the sensor have done, it's checks out. Okay, so let's take a just refreshing the problem. Okay, you have two templates. We try to simplify the system. We are not considering any of the other templates, N or J. We are considering only N and M. There are 4 wells in one and 3 wells in another, and they are producing from different reservoirs. So you always have a risk. When you have a field producing from the same reservoir, wells might be slightly different, but they are depleting the same layer. Okay? All of them are exposed to the same, in a sense, reservoir pressure. When you drain it, all the pressure will go in all wells uniformly. But in this case, it's a bit more risky, and that's usually something you have in multi-field systems, that they are going to deplete in a different way, and that causes some complexities that we have to take care, okay, that we have to take into account. So the first part of the exercise was, task 1 was basically to look into that. You have natural depletion, and now you have to keep track of not only one delta P of the choke. We are assuming all wells in each template are identical, okay? But you have to carry two, one delta P for template L and one delta P for template M. Okay, and that was not much of a problem for many of you. Okay. After, so we have, maybe pull the I'm going to take, I hope it's okay with you, but I took some of the of your charts. Okay, so that was the profile simply with the initial splitting. Okay, we said was 67, I think, and 20 or 27 and 63. Okay, and we see what happens initially is that you have the first one that enters decline. So the first template where you have a negative pressure across the choke, delta P across the choke, is template L. Okay, and then you start declining. If you don't do anything else, you don't compensate production from another template, if you don't add additional energy, the whole field is going to enter into decline. Okay, no choice. I have to go into decline. So that's the first part you see here, and it has some slope that you will see some decline trend. And after you reach a point where the delta P across the choke of template L starts becoming 0 and negative, that's where you have the second slope. And you see the slopes, basically they have a different, like a different constant, decline constant. Okay? Now, the intention, I try to make things easy for you, and I think I made it a bit complicated. Okay, which happens. Okay, problem 1. Okay, in real life, so remember this thing. When I give a rate, if the rate is feasible, that means that the delta P across the choke is positive, or the delta P across the pump is positive. It's that means that I can produce the rate. Okay, so I don't have to make network solving. I simply have to fix the rate and verify if pressure upstream is greater than pressure downstream. I don't have to do any flow equilibrium. But if it's not, if it's negative, then I have to do iteration. Okay, so that's something you should also have very much present for the exam. Okay, if delta P positive, no need for iteration. If it's negative, if I have to make flow equilibrium, I have to make iteration. Okay? And what I tried to make was that you will use, like we use in the oil companies. Okay, we have one program which might be Eclipse, might be Enval, which is taking care of the time decline of the reservoir, and we have one program that takes into account the network, that makes the network calculations. So that's what I try to make here. Just in this data, you make the production profile. You have, so you give the rates from the network. Okay, you calculate the rates here, and then you use them here to calculate the next step. Then you go back with that reservoir pressure, you calculate on this program, and then you go back. But turn out that that was more complicated than do it everything straight in this sheet. Okay, so I think I'm also glad that you found that out by yourself. Okay. But the idea was to make you, that you have to go to a different software, to our external software, to make the calculation of rates and then bring back. Okay? And the idea is that after, so at this point, so remember we have, let's make, we have a choke, and here we have 5, but I'm going to put just one, template L. Then we have this tau head, and then we have the main line, which actually are 2, but we can just simulate 1. And then we have, okay, and template M. So if I'm producing in plateau, right, we have our equilibrium point. Let's make it here, equilibrium point in plateau. Okay, I just choose it to be here, exactly at the wellhead, and I have to come to that point. I have to come from the reservoir all the way to the wellhead. So I have to come co-current using line P2. Okay, and then I have to come back with line P1, which is easy because I have the rates that are to be produced by every template. Okay, I have everything I need to make the calculation. At some point in time, this delta P, so let's take the second condition, that is that template M enters in decline. Okay, that means the delta P of the choke becomes less or equal than 0. Okay, and at that point, basically what many of you did, which was a very clever choice, so you don't have to change, you don't have to use the network simulator. Okay, okay, tau head, and so you left the equilibrium point in the same place. You know that you still are able to produce Q of template L. Okay, so you fix that rate. That will be 6.3, okay, million. But now you say the delta P of the choke has to be fully open. Okay, so I'm forcing that to be 0 by changing Q of template M. Okay, so they choose that equilibrium point. You're still choosing that equilibrium point and that equilibrium point. But now the rate simply is not known, the rate from M. You're simply changing it until exactly you have delta P equal to 0. Okay, which was a very clever way to do it without using, you know, this sheet here. Now, when you go to the third phase, and the third phase is template L enters in decline, you also did something very clever. Okay. Wait. Again, you left the same equilibrium point, so you don't have to change it. Okay, you took this one. Okay, but now you're saying the constraint that I don't know QL and I don't know QM, but I know the delta P choke of L has to be equal to 0, and the delta P choke of M has to be equal to 0. Okay, so I just change that, iterate, and I know many of you use the function, many of you used, which was also clever, either using absolute value or even using the square. Okay, most of you have used the square. And I think there was no big issue there. I think most of you got that correct. Okay. Now the next question was, because these two decline at the same time, decline at different time. Okay, so that's the whole reason why my plateau only lasts for 6 years. Okay, so what I was telling you, neglecting the constraint on the sand production, we have a limitation on the production of L, I think. We cannot produce more than 6.3, okay, or 6.8. Neglecting that condition, what is a better splitting simply to prolong the plateau? Okay, and what you have to think is that, well, the plateau will be prolonged if both of them enter in decline at the same time. Okay, because if one enters before the other, that means that I stop plateau. Okay, I end up the plateau. So that was a trial and error. You know, you had to increase a bit more because L is actually longer, can produce for longer time. So if you produce more from L, that will give you, this will be lower and it will decline later. It's simply like some, it's logic. It makes sense. Okay, and I think the splitting that worked the best was 73%, okay, for L. Okay, and that gave you 2 more years, so it's significant. Okay, not only, remember, in this case, maybe we are having, in both cases, the same ultimate recovery. We are recovering the same amount of gas. Okay, but the thing is that I have accelerated the recovery. Remember, all the thing that I gain extra, I'm getting it earlier. The discount factor is bigger. Okay, it's there is not much discount, so that is actually helping the NPV. Okay, so in that case, I think the solution many of you found was 0.73 and 0.27 for template L and template M. Okay. We didn't discuss here in class, but you can do the same. Try to do the same on a field. In this case, it's like there were 2 different reservoirs. Okay, so this is reservoir. How was the name of that reservoir? It was block 14 and block 13. Okay, so 13 was block 14 and that was block 13. Okay, so it's like there were 2 different reservoirs. So one example we didn't cover in class, so for systems, okay, you also have to choose, if you are interested in producing at a certain plateau rate, you also have to take care of this issue. Okay, you also have to make all of them decline at the same time. Okay, let's say you have, and there was a problem some years back, okay, where you have a few reservoirs producing to that line, to a common facility. You have field A, and you have field B, and you have field C, and the main, you wanted to produce a constant rate of oil with time. Okay. So when you do it in a multi-field, one approach that works, at least to have a first estimate, you got the idea, you have to split production according to the potential, right? So let's do it for two fields, okay? Only field A and field B. Okay, when two fields or reservoirs. Okay, remember we had a curve that tells me that is the potential of the field, okay, the production potential of the field. So it's how much I have produced from A, the cumulative production, and then I have also the production potential of A. Okay, and that can have, if I don't have any pressure support, or if I have, if I might have, it usually goes, you know, some just simply declining, okay, going like that. Might be linear, non-linear, whatever, okay, NPB. So that tells you very logically that the reservoir, when I produce more and more, simply can give me every time less and less, okay. When I want, let's say, I want certain field rate that I have specified, field plateau, okay. That is given, okay. Then I have to have a splitting. How do I split between A and B such that they decline at the same time, okay? So let's say I make an iterative process. I can make it through an iterative process, and then I choose Q plateau of A, right? So Q plateau of A will be here, okay? And then I read this NP star of A. And remember, we are operating at plateau period, therefore the time simply will be, how much is the time? The end of the plateau for A will be NP star divided by Q times the number of days per year, right? That tells you the duration. If you have the curve, if you have managed to pre-calculate reservoir simulator with the material tank approach, you can find out, try to estimate how long that plateau will last. Okay? And then you can say, if I already have QA, I already have then QB. Okay, Q plateau B will be Q of the field plateau minus Q plateau of A, right? Because what is not produced by A will be produced simply by B. Okay, so I come now with that number and I read Q plateau and I read NPB star, and then I say simply the Tn of plateau for B will be NP star of B Q plateau B times the number of days per year. And if you want to maximize the plateau duration, these two times have to be the same. So there is an iterative process in which I change QA until all of them, until these two become the same. Okay? So I can do a first estimation using the potential. If there are two separate systems producing to the same platform, to the same facilities, I can make that estimation. And actually in the compendium you have one example you know, what happens if it's a straight line. Okay, it's here, you find exactly the same. Okay, and then you substitute this linear equation. You assume the potential is a linear equation, which is good for undersaturated systems or systems where I have water injection, and then I find out that's the solution. Okay, that gives equal plateau duration. Okay, but you can also do it by trial and error. And actually, there was an exercise a few years back. Maybe it was even given last year. Let's see. This one, maybe it's here. It was not this year, it was maybe 2017. Yeah, I think it's this one. So this exercise, which is 2017, exercise set 3, is actually dealing with that problem. Okay, it's a field in Saudi Arabia called AFK, which is a mix of three reservoirs, three different fields that are producing separately with separate lines, and you have to give some planning, how much I should produce from each reservoir. Okay, so if you want to just have an exercise of what we explained in class, you can look into that. Okay, but also you have to be this approach, okay, so trial and error or using some sort of equation, but also you have to always, let's put here a small note, be careful with constraints. Okay, because you might have constraints that don't allow you to reach that number, that Q plateau. Okay, one thing could be excessive. You will produce too much drawdown. You will produce just too much collapse of the wellbore. It might be that maybe that field has maybe, let's say, it's very heavy oil. Okay, so the blending that you have at the end, it will be, that's exactly this exercise that we have here. Okay, one of them is very productive. It's has a slow decline, but the API is very low. Okay, and very low is 28, something like that. Where is it? Okay, 31. It's what you want to get here from that crude, which is it's sold with the name Arabian Light. Okay, but one of them has an API of, I think one is 32 or 35, 36. Okay, and the other has 27. So you want to be able to sell it to the market, you have to sell it with this API, 31.8. That's what the customer, that's what the refinery, everybody is waiting. Okay, but if you produce too much from this Khurasania, if you produce too much from that one, then the API will go down. That's not something you want. Okay, so be careful with the constraints. So the constraints could be maximum production per well, okay, or you can also have some due to API blending. If we talk about gas, it can be CO2 or H2S content. Okay, all kind of constraints that you have to be careful. So you can find ways to prolong the plateau, but be careful with the constraints. Okay, if there are any operational constraints. Now there was a few groups that did something more creative that I think was also very nice. So instead of fixing the splitting from the beginning, they tried to increase it after they reached the end of that plateau. Okay, they decided to increase the production from L, and then when the production from M was reducing. Okay, it's also another way to prolong the plateau. But keep in mind, operationally, we like to have operators in the field like to have stable things. They don't change. I just keep opening the choke, opening, keeping the rate the same. When I come into this approach, I have to be sure that I'm increasing, ramping up the rate for some wells. Okay, and the operator might not be very happy. Okay, but it's a very valid way to do it. Okay. Okay, so let's go now to task. That was task 2. So task, sorry, that was 1 and 1.A. So that's task 2 with the compressor, simplified compressor. Okay. And basically we had a system that and also here I've placed a compressor here on the line. Okay, so that's template L and template M. So before you do any calculation, what should the compressor provide you, intuitively speaking? Okay. Remember, the recovery factor depends on how much back pressure I have in the wells. Okay, if I can go to a bottom hole pressure very, very low, I will get more out of the reservoir. Okay, or I can keep a low pressure that basically I can delay this minimum flow. Okay, so I can produce more and more higher for longer time. So that means the compressor should give you some higher recovery factor. Okay, because of the reduction in back pressure. Okay, but most importantly, the compressor accelerates production. Okay, and that by means of either prolonging the plateau can also simply the tail production can be slightly higher than if you didn't have a compressor. Okay, so higher values during tail production. Okay, and that effect is extremely important. And was one group, or I think maybe two, they tried to make an economic analysis of how much this production represents. Okay, what is the value of this additional production? But simply it's very important. This one gives you higher NPV by recovering earlier. Recovering gives you higher NPV. Okay, and in general it's better for the project. So some of you were saying, well, we are not able to produce for 25 years now. We will produce in only 18 or 20 years. That's actually something positive. If you manage to recover exactly the same amount in shorter time, that's what you want. Okay? So how did we make the calculations in this example? Okay? So we had exactly the same setup. Okay, we had a rate given, QM, QL, and if you can produce the rate without using the compressor, you do it. Okay, simply natural production. So initially, let's say time 1, natural production. Okay, that means both chokes are positive, and that means I don't need at all any compressor during that period. I can simply produce, I can even put a bypass line. If the compressor is in place, I can simply put a bypass line to bypass the compressor. I have to put 2 isolation valves Okay, but that might be an option. So what is the first thing that happens? Exactly the same as the other case. Okay, delta P, or let's say template M, enters in decline. And here we have to be careful. It wants to enter in decline, but we are not going to let it. Okay? So we have we have still this guy. Okay, we have QL. That's the value that was given. Okay, let's call it maybe with a P saying plateau. Okay, but now we know this choke now is fully open. That means it connects the wellhead. It completely connects the wellhead to the towhead. Okay, it simply makes, in this case, the choke can compensate, is breaking the connection, is breaking, and it can really adapt for any delta P, positive delta P, to make sure that rate will flow. Okay, but for the other case, I fix now QM. Okay, even though I'm not sure I will be able to flow, but I fix it, the same name, the same number I had from before, and I move from wellhead to template, and I move all the way here to towhead. Okay, because I'm saying it already entered in decline, this choke is fully open, but if I was producing this rate, okay, if I was producing that plateau rate and it was fully open, I will get some pressure here. So I come all the way and I calculate that pressure. Okay, this P towhead. So P towhead is calculated a co-current from M. Okay. The next thing, now I have to verify. Okay, remember with compressor and choke I can have many operational conditions. Okay, so I have to verify. The first thing is that I have this rate, I come here, and I have that pressure and the rate, and I come here, and then I verify that delta P choke of L is positive. That means that by choking, and you will see actually I had to increase a bit the choke compared to the end of the plateau. Okay, because that pressure simply declined. Now the towhead has to be much lower. So as the first step, A. Step B. What is the last step? I have to calculate the required pressure at the discharge of the compressor. Okay, so C is P discharge calculated from P sep. Okay, counter current. And then the last step that I want to see if that's feasible or not, then I have to verify that P discharge minus the P towhead first has to be positive, right? Has to be negative. No, a positive, that's greater than the other. And then also, according to our restriction, P discharge minus P towhead has to be less or equal than 50 bar. Okay? So far, good? Yep. Okay, now let's go to the third step. What happens next? I continue. I think you could produce for maybe 2 or 3 years, but then at some point delta P across the choke of L. And remember, we are keeping this choke, we are still choking, which is a bit strange, right? We are adding energy and then we are removing energy here. Doesn't make much sense, okay, to give energy. It costs money to give energy and then to take it, okay? But here we have the constraint that this has to be less or equal than 6.7 e to the was 10 million, right? Standard cubic meter. Because of some other reason. So we cannot go over. So even though it sounds crazy, that's the reason. We have to honor that constraint. Okay? Then the third case that happens is that delta P of the choke becomes less than 0. Okay? Fully open choke. Okay, so let's do again our and here we have to note something every time I make the system smaller and smaller. Okay, it's not, the pipeline is not getting shorter. We have to note something. By at this point in your calculations, delta P from the compressor is already equal to 50 bar. Okay, you see that you reach very quickly. Actually, if you plot the delta P of the compressor, initially you don't need any compressor, okay, but then you start needing it and then goes very quickly to 50 bar. Okay, that means really to suck that fluid, that this rate from M, you really need to lower that pressure very, very much. Okay, you need to lower it. And of course, at some point when you reach that bound, if you plot the rate of the field, okay, the rate of the field was able to keep in 10, okay, but then at some point it started to decline. Exactly when the compressor cannot give you more energy than what you need to maintain the plateau. Okay? Okay, so what do we do in that situation? Okay, this one is fully open, delta P 0, and this one is fully open, delta P 0. Okay? But we have really no idea what the rates are, right? The rates are, now it's equilibrium, QL and QM. We have no idea. Now that the rates are, I lost control of the system. When I open these two chokes, I lost control completely of the system. Okay, and it might even happen that I will have backflow. Okay, so anything can happen in that system. Okay, so one way you guys solve it, okay, is you assume, the first one is assume QL and QM, okay, and this you assume a value which is less than the plateau, which makes sense. Okay, you assume a number slightly lower because now you won't be able to maintain the plateau. Okay, with this number you calculate P discharge, and this is counter current from separator. Okay, so you came, that's the second step, you came all the way from here to here. Okay, the third step, and this was a bit tricky to understand. Okay, you want to find, always you want to get as much as possible from the reservoir, as much as possible from your system, but honoring the constraint, okay, honoring the 6.7. But maximum Q of the field is obtained when delta P of the compressor is maximum, right? That's the maximum energy that I can give to my system. And that's the key thing to understand in this approach. So they say simply, I can calculate P tau head has 50 plus P discharge. Okay? And now I have reached this point here, P tau head. What is the next point? I have these two rays which I have assumed, right? And then I move all the way here and all the way here, and I check. Are they equal? No. And then I repeat once more. Okay? So then I say move co-current to P tau from M, L and M, and check if P tau head is equal to P tau head has seen from M and equal from P tau head has seen from L. Not minus but equal. Okay? Are they the same? That means that they are all in equilibrium. The whole system, the two rays that I assume here, they are in equilibrium. Okay? If they are not, so let's put here yes, then I have a solution. Not, then I have to repeat again. Then I have to repeat again from the beginning. Okay, and then that's how I have my solver. And people have different ways to set up the solver. Basically what they did, they iterate until delta P was exactly equal to 0. Okay, so they put actually these 2 points. Some other approach is that instead of calculating, let's call it 4 prime, and then we take a break. Okay, 4 prime is move counter current, which is also another valid approach. From P tau to P template M, and from P tau to P template L. Okay, and then you have to move co-current from M to P wellhead M, and move co-current from L to P wellhead L. Okay, and then I verify that delta P M is equal to 0 or delta P L is equal to 0. It's exactly the same thing. Remember, it doesn't matter where you put the equilibrium, as long as in that case the delta P of the choke is 0, and if you calculate tau head from both sides, they give you the same. Okay, but it doesn't matter where you put the equilibrium. Okay, more or less clear? Yeah.
I think the tau head is discharge minus 50.
P tau head is,
Because P tau head
Should be plus.
yeah, it should be here. Yeah, we fix it. P discharge is usually higher, so I say minus 50. Okay, then you get tau head. Is that correct? Wait. Okay. So I say now let's take a break, and when we come back, you guys are going to work a bit, just that I'm not myself just trying to explain, okay, but you're going to get an exercise that was actually in the exam of 2016, okay. It's exactly the same, looks familiar, exactly the same system, but now instead of equations you got a plot, okay, for each template. And we are going to neglect really the flow line. We're going to assume simply the choke is very close to the tau head, okay. But you'll have to solve that graphically and then we are going to discuss it here. Okay, just to make sure that all of us are on the same page. Okay. But then let's first take a break. Let's come back here. So the first task is saying we want a rate. In that case, we like the plateau period. We want 9 million e to the 6. Okay. We know probably the system won't be able to deliver that. Okay. Simply, if we put these three together, okay, where is the problem? Okay. If we put with no compressor, if we put all of them together and it gives me more than 9 on 9, we don't need a compressor. Okay, so be careful. Might be a bit tricky. You might get a tricky question in the exam. Okay, but in general, that's how it should be. Okay, so the first thing we go is for the easiest. Okay, we know here you have to have circulating 9. Okay, so you have that curve that tells you the required pressure here for the pipe, and you have the rate. So you can simply say, what is the required pressure I need at the discharge of the compressor? So that's like the best and the easiest route. Okay, so I found 9. Go up. Let me maybe make it in red. Okay, and I find, some people say 67. Is that the number? Okay, so you know this is something that is true. The discharge of the compressor has to be exactly 67 bar. Period. If I want to have that rate, that's how much I need to push the fluid against the separator. Okay? Now comes the tricky part. From these two, the two rates, QM and QL, should be equal to 9. Okay? But we are not sure what pressure we need. Okay? So you need to do some iteration. But however, both of them, if there is no choke, okay, both of them are exposed to the same pressure. They have the same suction pressure. So what you have to make is an iterative approach saying, okay, so that's the first step. Second step, assume. And what are you going to assume? You could assume the rates, right? But an easier way is to assume the pressure, which is common to both. So we're going to assume pressure at the junction. What value do we assume? Well, we know it should be less than 67, right? Otherwise, we wouldn't need a compressor. Okay? But let's see, maybe we can start something around 20. Okay? So if I put 20, that's my first iteration. How much is that? Like 69, okay, 6.9, 20 bar. And the Q from L is 6.9. I think so. And how much is Q from M? That is 2.65, right? Okay. How much is the sum? 9.5. Okay, so we slightly Q of the field is 9.5. Okay, so it's slightly too high. So I have to repeat, do another pressure. Who finished? What is the final pressure? 24, 28, 20, 36. Okay. So you try 2, 4, 6, right? And that gives you 2.35. Yeah. Then I assume once more PJ 36 bar and QM will be 2.35. Okay, and QL will be 36, that should be 24, 28, 32, 36. Yeah, 6.6. Yes. Close enough. Okay. I'm not going to ask in the exam to be minus, 1 to the minus 2. Okay. So that's fine. You found that's the solution of actually the first task. You say that is possible. Yes, it is possible. And the delta P of the compressor should be equal to 67 minus 36. Okay, which is
31.
okay. Period. Point. Now we go to the next task. And the next task is a bit tricky because we are including the effect of a choke. Okay, we are saying which actually I have in the field. Okay, I have a choke in that template from which I can control the rate. If for some reason I'm not satisfied, I'm not happy with the rate that comes from that template, I can use a control valve or a choke to regulate. Okay, and in this case it tells you if in case 1, in task 1, the flow from template L exceeds 6.4, that's the limit I have now for sand production, which is similar to the one we had in the exercise, okay, in class. There might be wellbore stability problems in the well. Okay, it should be to the 10, okay, 6.5 to the 6. Okay, so that means you have to choke. Okay, the template L can produce much more, but you have to choke it. You have to choke it back to 6.4. And we have 6.6, okay? Okay, so what do we have to change? I still want to produce 9, therefore, so let's put here task 2. Okay, so still P discharge is going to be 67, right? Because that's only a function of Q of the field. And Q of the field, we are trying to keep it at 9. That's, what we want to produce. Q of the field is 9 e to the 6. Okay. Now, we want to limit. We know L can produce more, but we're going to limit. So we're going to say Q of L will be all the way to the upper bound, will be up to 6.4 e to the 6 standard cubic meter per day. So we come and we say 6.4, that will be actually here, I think, right? Well, and how much is that pressure? 40? 42?
41.
Okay. 41. So we have P. What pressure is that? Be careful here.
P1 head?
That's, if we assume the flow line is very short, we assume that control valve is the choke, okay? Then that will be the wellhead pressure, okay? Or it could also be the pressure upstream the control valve, okay? It's a long name, control valve. Or it could be P wellhead, okay? Also, depending what are you saying, if the flow line is very short or if the, if it's simply, so that will be 41 bar, right? Now, how do I define what is the pressure of 2? Okay, what is the pressure of M of M? And here is, you have one more equation that you can use. You know the rate of the field is 9. You have this, which is 6.4. Okay, and then the rest simply has to be produced by M. Okay, and we know in the previous case, M was producing 2.35, right? So now we have to increase it. So we know the pressure cannot be 36, but it has to be lower than that, okay, to get the difference. So what is the difference? Q of M is 2.6, right? Okay, so I come again to the plot. That's what M has, if this situation works, that's what M has to produce. So I have 2.5, I have 2.6 here, and I have, what is the pressure that I need at the tau head? Okay, 24. That pressure will be the pressure, no matter how you want to call it, pressure at the wellhead of, this is L, this will be the M, or it can be the pressure at the junction, because it's open choke, okay, I don't have anything in between, and that will be, I forgot, what was it, 24?
24.
Okay, so how do we make sure that everything makes sense at the end? We have to verify that we have enough energy and everything makes sense. It's physically possible. First, we know that the delta P across the choke that we have of L should be positive, right? And how much do we have here? 41 minus 24, okay? That's 17. Okay. Then we have the other condition, which is choke of M is fully open, okay? But we have the other, that the delta P of the compressor should be greater than 0, okay? And that means 67 minus 24, okay? That gives you how much?
43.
Okay. And then you finally make a check compared to the other case. Okay, in the other case we had delta P of 31. In this case we have increased to 43, and the reason is simply to drain more fluid from M while keeping L fixed. So we are giving energy to L, but we are burning it in this choke, and we are giving energy to M simply to get more out of M. Okay? Very easy. You can do it, in only a few minutes. The thing is that it should be, to test your knowledge. Okay, it should be to make you think. Not so much on the calculations, but more on the if you understand the problem. Okay, so I think we reached the end. Unfortunately, we didn't cover all the things we wanted to cover. Okay, so next class tomorrow we are going to look into the compression map, how it looks like. There were some challenges there, and then on the exercise 2, and then hopefully we will try to have an exercise also tomorrow, okay, in class. Okay, before we close, any question? No. Okay, see you tomorrow. Then.
Milan,
Yes.
can you go to the end of the notes?
Okay.